Okay, so this is the second video in chapter 3. So in the previous video, I introduced you why we need a measure of central location. So I said, basically, it helps you make an easier decision and more like rational and objective way of making a decision. And so as the most typical, most common measure of central location, we are going to study the average. So before talking about the average in detail, I will first set up the terminology. Actually, there are different names for the same thing, like the average, the mean, and the expected value or the expectation. Um, at least in this course, at least at the college level, I believe they are the same thing, right? So the average is just a casual way to talk about the average, and the mean is more statistical terminology, right? Specifically to the mean. And the expectation is more like mathematical term because you can think about like we usually say when expectation, like you can think about expectation of x squared, expectation of x plus y. So like when I usually refer to some mathematical operation of more complicated form, then expectation is more like natural. So, but and like simply speaking, they are the same thing, right? Don't worry too much about that. But the notation follows the expected value. So I'm usually like almost any like mathematical notation uses this form, expectation of a random variable. So it is a mathematical operation. If you input a random variable, it returns the expected value of that random variable. So instead of x, you can include like x squared or x plus y, like other different forms. So you can understand it as a kind of another function. Um, so anyhow, I have a tendency to say it as expectation, right? Because like in my research, I usually call this expectation. So, but basically they are interchangeable, at least within this course. Okay, let me start with another example, trick example. Suppose that there is a lottery and it's like probability distribution is like this. 99% it's nothing, but 1% you can win $100, right? So of course, actual real lotteries are more like extremely small probability with extremely large prize. But let's simplify the setup like this. So then I'd like to calculate the average price, or usually we call this like expected gain or expected price. Then I say there are two possible outcomes, $0, $100. So I will like, and so the average is the middle in between them. So it's $50. Is it right? Think about this. So because there are two outcomes, 0 and 100, we can take average between them, $50. This is wrong, right? Because like because it means when you add them and add 0 and 100 and divide by 2, that means you are treating these two outcomes equally, which is not true because 0 is much more likely to happen than $100. So this is wrong. And you may laugh at this thing, but from my experience, if I make this question in the exam, literally like 1/3 of students choose $50, right? So, and it could be you. So don't laugh at this. Anyhow, it is wrong. I believe you see why. So $100 is much less likely. So you have to put less weight on $100 relative to 0, right? So here comes the definition, right? You have to understand this definition. Mean is the sum of probability weighted outcomes. So it is some kind of like a mathematical operation of the outcomes, somewhere in the center of the outcomes, but the center is calculated as the probability weighted. I wanted to say it is a probability weighted average of the outcomes, but I cannot use average to define an average. So, but more in like easiest way to explain the average is that it is probability weighted average of outcomes, right? Like given that you understand what average means. Okay, then and also and then the reason why you are confused, why some students choose $50 here is because they don't distinguish, they cannot tell the difference between raw data and summary table, right? Raw data, from our previous example from the first video, there was a student with 10 grades, and if you list 10 numbers, that's raw data. There was no process on these numbers. It is just literally unprocessed numbers. But if you process it once, then you get frequency distribution table. Like I summarized 10 numbers into this table, so we just count how many observations for each grade. So this is a different information from the raw data. So depending on what kind of format you have, the way you calculate the average is different. Let me show you. I will explain one by one. Now first, when you have raw data, it's easy. This is what you usually see as the average. So but I am going to approach from the definition. So the mean is the sum of probability weighted outcomes. Suppose you observe n numbers. Like previously we observed 10 numbers, and now so we have in general have n different observations, and like first we have to weight those outcomes. We observed n outcomes and we have to weight them using their probability. But there is no probability, right? Like we only have numbers, outcomes, no probability. So our hidden assumption is that we assume that all observations are equally likely, right? That means they have to receive the same weight, which should be 1 over n. Because total probability must be always 100%, right? So and we have n observations, so divide 100% by n and assign to each of the outcome, right? So you may understand this like the average in this way. The first observation is weighted by its probability 1 over n, and second observation is weighted by its own probability, which is the same 1 over n, and the last observation, last outcome, also weighted by 1 over n. So all the outcomes are equally weighted from the implicit assumption, right? And then you can just factor out 1 over n. So in the end, it's like sum of all the outcomes divided by the sample size. Or in general, we denote it as summation like this. So this is the typical average you have in mind, I believe, I guess, right? So this is right when you have raw data. And this is also like usually it is explained as the sum of the outcomes divided by the sample size. That is right. That is the right formula. But I want you to understand the underlying definition and where this is coming from, right? So because the reason is because if you just take it as the sum of outcomes divided by n, then that formula does not work for the other case, right? Here, back to the example, just this is how you calculate sum and divide by the sample size, but more important is the definition. Sum of probability weighted outcomes, okay? So I believe this is super easy, right? Now the main problem is when you have probability distribution table, right? Suppose that you have probability distribution table. By the way, when you have a frequency distribution table, it is not that difficult to transform frequency into probability. We learned that in chapter 1. So I assume that we already transformed frequency into probability. And then the idea is the same, the definition, sum of the probability weighted outcomes. Probability weighted outcome means you have outcome, you have probability, and then multiply them. That is probability weighted outcome. So for the first outcome, you get probability weighted outcome by multiplying the probability. And for the second outcome, you get another probability weighted outcome. Of course, now you have to multiply the probability for the second outcome, right? Like for the first outcome, you have to multiply probability for the first outcome. Likewise, so multiply row by row, right? And then you make another column which collects the probability weighted outcomes. And then, so we calculated this part, and you have to sum them. Sum all the probability weighted outcomes. So mathematically, you can denote it this way, right? In this case, I don't know how many observations you have. Like there can be many possible outcomes, but doesn't matter. It depends on the example you have. So back to our example, we have frequency distribution table like this. And first step, you transform the frequency into probability, right? Because we observe 10 outcomes, divide the frequency by the sample size 10. So 1 over 10, 0.1, 4 over 10, like 40%, 0.4, likewise, like we get probability. And then make another column to multiply the outcome to the corresponding probability, right? So A flat at 4.0 happens 10%. So multiply and then you get 0.4. Like A minus happens 40%. So if you multiply that, it will become 1.48. What is interesting here is 4.0 is greater than 3.7, but when you weight their probability, 3.7 is more important, is larger than A. Like A minus is more important in the average than A flat because it is 4 times more likely to happen. Likewise, like even like B plus is 3 times more likely to happen than A, so its weighted outcome is greater than that of A, right? So in this way, you get probability multiplied by their outcomes, and finally, you get another column. Finally, you sum these numbers. 0.4 plus 1.48 plus 0.99 plus 0.6 plus 0, you get 3.47. That is the mean. This is how you calculate the mean, okay? Right? So again, as I said, if you understand the definition, the mean is natural, right? But the problem is if you learned that the average is sum divided by the sample size, then it does not apply to this case. So that's why definition is important. Definition is more kind of unified framework to understand different things within the same framework. So I'd like to emphasize that. And finally, I want to think about this. Sometimes you have sample so in this case, you have 10 observations, right? So 10 observations, you may use this approach or this approach. Does not matter. You can calculate the average directly from the raw data, or you can calculate that from like probability distribution table. That does not matter. Both are the same. They should give you the same average. But some cases there is no raw data. For example, when you think about dice roll or coin toss, we know that like the probability of 1 is 1/6, and like probability of 2 is half, like 1/6 again. So 1, 2, 3, 4, 5, 6 are equally likely, so they are 1/6 without observing any observations, right? So we are going to assume that that is the case where you have infinite observations. Like if you actually throw a dice, you are not going to get 1/6 at all, like because it's random. Even if you throw like 600 times, the number of ones may not be exactly 100 times. It could be 99, 101. So the true probability is a limit mathematically. So when the number of observations is infinity. So then, based on this idea, we would like to distinguish the population mean and the sample mean. So the population mean is when you have true probability, like or when you have infinite observations. Of course, it's not possible, but conceptually, if you have infinite observations, then you have the true probability. So the mean calculated based on the true probability is the true mean, right? That is the true mean. And this true mean cannot be calculated from the raw data. As I said, you have to have infinite observations. That is not possible. So population mean is the true mean, which is purely which is our mathematical target, our target of estimation. We'd like to estimate this true mean. On the other hand, the sample mean is what we calculate from data. As I said, our observation is finite, and because in finite experiments, your outcomes, your observations may be random. It's random, right? So it may not be the correct probability, right? Like coin toss or dice roll. Your probability in like 1,000 experiments may not be exactly 50-50 in coin toss. So there is random errors, but however, you may calculate that. So population mean is the true mean, but we cannot calculate. But the sample mean is random, but we can calculate that. We can calculate the sample mean. So it is important to distinguish them because later in estimation, our goal is to estimate the true mean using what we calculate, right? So their notations are different. Mu is the Greek letter mu is usually denoting the true mean. And on the other hand, what we calculate from the data are usually denoted as x bar, and it usually denotes the means of estimation, or what we try, like our guess of the true mean is the sample mean. So even though both are kind of mean, but their properties are very different and their roles are really, really different. Both are important. So I want you to distinguish them here. And if you understand these two different ways to calculate the average, then I believe it helps to understand the differences between them, right? Okay, thank you for watching. Next time, I'm going to make the case a little more complicated. So far, it was too easy. Like I believe you already know how to calculate the average. I just recap the definition. But next video, it will be a little more tricky. Okay, see you there.